So there are some transformations that are not linear transformations. And as an example of that, maybe we'll take a look at r times cosine theta, r times sine theta. And because of this particular program that I'm using, I'm kind of stuck to using x's and y's. But in other forms, you might want to take a look at this transformation as r cosine theta and r sine theta, where it takes r and theta as your input variables and then spits out an output variable. And for those people who have taken Calc 3 before, what would you expect to happen for something like this? It'll get you what they call a polar coordinate graph. And so what happens here is that I would take the I would take that box, that square, and then I would have the x-axis represent my radial distance, and my y-axis represent my angle as it draws out a circle. And I also left the grid on the left-hand side there so you can see what happens to the grid as it goes on the right-hand side. So this is where you take your graph paper full of squares, and then when it translates into polar coordinates, the graph paper becomes circles with radial distances. So we can try to control or adjust our domain and see what happens to it. So let's say A we'll adjust A and we'll adjust B. And then we'll let our domain, instead of going from 0 to 1, we'll let it go from 0 to A and 0 to B. So that when we adjust, uh-oh, what's going on? Yeah, I put it here. Oh, we still have an angle of 0. There we go. So if I adjust my A, remember A is my adjustment in the x-axis, and we said x is going to be the radial distance. As I adjust my A, my x values, my radius gets larger or smaller. And if I adjust the B, which is the y-axis, which I said was the angle, adjusting the B would make the angle move in your radial measurement. So this is not a linear transformation for a variety of reasons, and I'll let you think about that. Actually, why don't you think about it? Nah, let's not think about it right now. You guys can think about that in your own time. So what I want to do is I want to go back and take a look at other linear transformations, and some of the linear transformations can be expressed with a matrix. So this is a kind of cool picture, though. We should have it in our notes. How much? So this is an example of a non-linear transformation. way too big. Forgot to adjust my page size. Sorry. Let's adjust the page size. Did it? All right, just some details about this. Some details about this example. We have a transformation that's not linear. We'll say x, y formally could look like r cosine theta, r sine theta. This is polar coordinates. And this is not linear. Now, in calculus, we would try to force it to be a linear transformation. So what we would do is we would go back and find derivatives. Remember, derivative is a linear transformation, and when we linearize something, we often use a derivative to describe the slope and stuff like that. So the derivative of a transformation is a little bit more complicated, and in fact, the derivative of a transformation is going to involve a matrix, interestingly enough. And so that matrix will help us linearize this transformation, so we could do things like take derivatives and integrals of things in polar coordinates. So that's an interesting aside, but let's go back to the idea of a linear transformation, and let's see if we can come up with examples of things that are actually linear transformations. So let's go back to this picture, and let's set A back to 1 and y back to 1. So we're looking at a square. Let's just put 1 here. So we're looking at a square domain, and we're interested to seeing what happens to a square domain when we pass it through things that are a linear transformation. One of the common transformations that they show you is this thing called a shear transformation. And a shear transformation takes your domain and then, I don't know, shears it. Distorts it in a way that's called shearing it, and it takes. Yeah, I don't know about that. That's, yeah. If we're gonna say diagonalize, you might as well say parallelogramize. Parallel. Yeah. See. Yeah. Parallelogramize as a parallelogram. In any case, so what we're doing is we're taking a look at this one form of shearing is taking a look at this value a here and changing that value from a 0 to another number. And so here, if a was equal to -1, the shearing is going to go towards the negative side of x. And then as we let a go from -1 to 0, we're kind of back at the identity. And then if we go past 1, we're shearing to the right. And so that's this is an example of a shear transformation. And the examples that they have, I think, in the book and other places, they actually have a sheep. But you can shear a sheep. Yeah, it'd be hard to geometrically shear a sheep, but you can shear a sheep. What did a sheep do to you? So this is a shearing function, a shearing transformation that shears the x, that shears towards the x. And this is what happens when you have the a equal to 1. And actually, if we want to to um, to write this as a transformation, the transformation will take an x, y, and then, um, well, let's see what happens to it. So that's kind of interesting. Um, how do you think we can represent this as a transformation? So the way to represent a transformation is you have to have an input, which is our x, y here. This is kind of like our input. And then our output is a combination of x's and y's. It's a vector. It's also a 2-vector. So the input is a 2-vector and the output's a 2-vector. So maybe we should say that. This is a shear transformation from R2 to R2, where we have an input and then we do something to our input and get an output. And so what looks like happens here is that the x value looks like it stays pretty much the same, except the y values kind of shift. So let's see, how can we represent that? And how far does the y value shift, I wonder? Let's take a look at a couple of vectors. Oops. Let's do it from here. Let's take a look at this vector. What's this vector? 1, 0, 1, 0. Which also happens to be your standard vector I in the I direction. So let's take a look at that vector and see what happens to this vector. I think it might also help if we actually see, I mean, it looks like it's clear what happens, right? It looks like that vector is going to get mapped into the same vector over here, which looks like it doesn't change much, if any at all. It looks like this vector I goes to this vector, which is again 0, 1 or 1, 0. Right? Now let's take a look at the other vector, the 0, 1 vector. Which is also known as your J vector in terms of your standard basis. And where does that go? That's the one that gets skewed. Right? That's the one that tilts. And if we take a look at that, I should have put the X and Y axis back. If I put the X and Y axis back, it looks like it's going to have a 1, positive 1, and a positive 1 value, right? So it looks like it may have moved to positive 1, positive 1. So let's just put that and say our J vector actually moved to another vector, 1, 1. I guess depending on what A is. What if A was equal to 2? How far do you think this will go? Yeah. The magnitude? I don't know the magnitude of the vector. The green vector, this green vector? I don't know if it would necessarily double. I don't know if that's the correct way to describe it. It would go further. Yeah, the first only one, only the first value doubles, but not the second one. So um, if this were to go to, instead of our A being equal to 1, if A was equal to something else, if A was equal to 2, we would probably expect our new vector to go to 2, 1, which doubles the first um, component, but doesn't necessarily double the whole vector. Yeah.
So that's coming from like the multiplication. We can, I guess.
Oh,
Perform the matrix multiplication. It does actually.
yeah, yeah. Where we're kind of seeing the matrix multiplication happen here. Um, which way? How?
If we perform the multiplication and then prove that it's linear that way.
Yeah, we could do that, but I think the first thing I would like to do is I'd like to see what happens to the actual to see how should I put it, to see how to describe the actual yeah, the actual what's happening. Describe the actual transformation is what I'm trying to define this transformation. And so what I'm trying to do here is complete this definition for this particular transformation. And I think what's happening here um, is that your y value looks like it'll stay the same. If you look at the y values, it looks like it'll stay the same all over the place. And then it looks like your x value is going to get stretched towards whatever the y value is. All right. So I don't know. Maybe I should have started with this first. Um, but for any value of a shear transformation can be described as this transformation t is equal to x plus a times y and y. So if I change this, so I used a matrix to describe that, and it turns out that I can use a matrix because it's a linear transformation. Um, but if I write my transformation as x plus ay and y, and then I say I could change the value of a any way I want, then I'm looking at a shear transformation. And this, in fact, is a linear transformation, which is what we're going to try to prove next. We do have a linear transformation happening here. And for that, let's see. Um, and we can make the value of a to be whatever we want. We would just, if we go past 1, the shearing will just get more slanted. So this is what we want to define as a transformation right here. And then now let's see if we can actually prove that t equals x plus ay and y is linear. So we'll prove that it's linear, and we'll take a look at the two rules that we had, or the two criteria that we had. We had t of can I change the symbols? I guess, do I have to change the symbols? So just to be consistent with the book, I'm going to need to change the symbols. So let me change the symbols to ax2, x1. So I'm going to change the symbols on you, and hopefully you can, negotiate that in your heads, what's happening right above it versus what's happening now. So uh, let's make a little note in our notes. So note our symbol change. I'm going to use x and y now as vectors, and then I'm going to use x1, x2 as one vector, and y1, y2 as our other vector. And so what we're interested in doing is finding out what this is equal to. Now this is equal to, in terms of the vectors themselves, x1, x2 plus y1, y2, and this is t of the vector x1 plus y1, x2 plus y2. Okay, so let's finally put it into our linear transformation. So in our linear transformation, x1 is actually x1 plus y1, and y, or x2, is actually x2, y2. And then our second component is x2 plus y2. So if we distribute and reorganize, we will get x1 plus ax2 plus y1 plus ay2 and then x2 plus y2, which I'll then split up. x1 plus a x2, x2 plus y1 plus a y2, y2. And this happens to be equal to the transformation at x1, x2 plus a transformation at y1, y2, which is t of x plus t of y. And from the starting to the ending, we see that our first criteria is satisfied. And then we'll do the same thing for constant times x. And it's just factoring out that constant. We'll see. This is t of c times x1, x2, t of cx1, cx2, because that's a scalar multiplication. And then using this formula now, we're going to put it in cx1 plus a cx2, and then cx2. And then it looks like we can factor out the c from the numerator, or not numerator, from the first component, and then factor it out the same thing from the second component, and then factor it out of the whole thing. And then we get c times t of x. Okay, so by going through that process, we see that we've satisfied our two criteria for it to be a linear transformation. And then we can also double check to make sure that all the other things that follow, is that the origin stays at the origin. And if we take a linear combination of these two, the x, so the I plus j, for example, and then we map it on, we're going to get the ti plus tj. But that's satisfied. This satisfies in the second one, or in the first component, or the first proof, whatever. Okay. So here is first actual linear transformation where we can see the pictures and we can see the linearity, and then eventually we'll say, we kind of did it backwards, but eventually we'll say that this linear transformation, if we have a linear transformation, we can actually represent the transformation with a matrix. And we kind of started, I kind of started with representing it with a matrix, but technically it should have gone the other way. Okay. Let me show you another shear in a different direction. Instead of having the AX here, or AY, we can shear on the bottom part. And then what happens there is that instead of the shearing to the left and to the right, it kind of shears up and down. Okay. All right. So there's different versions of the way we shear this. Yeah. I'm using a program called Graphing Calculator. If you want to look it up, I can post it on our Canvas site. It's not free, but if you're really interested in doing it with this, then you can pay for it. Yeah. Well, yeah, if you read ahead, that's probably what's going to happen. But yes, that's what's going to happen. We'll get there in a minute. So we could do a double shear. So we could do both shearing to the left and shearing left, right, and then shearing up and down, and then we get something like this also. You know, you get some interesting shearing when we're doing this. There's another. Oh, there's another. Another transformation that's kind of like scaling. where you can scale horizontally and or vertically, or you can scale at the same time. Um, and we can do a couple of examples of those. So let's take a look at some scaling transformations. I'm just going to call everything t. And the basic scaling transformation is multiplying your input output by a scalar, one scalar, and then that would make everything go larger or smaller depending if c is bigger than 1 or less than 1. But there are other sort of scaling transformations where you can just scale one of them or scale the other one. Or you can scale each of them separately with different values. So if they happen to be the same values, if A and B were the same, then it's like this first scaling, and that's just going to scale your domain in the same direction, same scale in the x and in the y direction, but you can scale each of those directions separately, individually. And we're not going to go through the proof, but you can imagine how the proof of showing that these are linear transformations by going through the process that we did with the shear. Other transformations, we should say. Yeah. Oh yeah, the A is not supposed to be in that first one. So the other transformation that I want to show you is called the rotation transformation, which is kind of interesting. It's kind of cool. And for that, I think I'm going to use the matrix version of this. And for that, we need some trig. Cosine, sine, sine. I think it's A. So when the angle is equal to 0, when A is equal to 0, we have essentially the identity. The thing goes to the same place. But then when we start changing the angle, we'll see that this is going to be a rotation. And remember that the origin has to stay within the origin. So that origin, the corner, the bottom left-hand corner stays where it's supposed to be, where it's supposed to stay. And the way this is set up, it's set up to rotate exactly by the angle that it's given, which is in this case A. But we can, multiply this by 2, and then it'll go twice as fast, etc. So there's this particular transformation for a fixed angle A, then you have a rotation transformation. So let's just copy this. So this is a matrix that describes a rotation transformation, and so we can try to prove that it's a linear transformation, but let's just say it is and be done with it. All right. Now, to address what Alan was talking about, the idea behind the linear transformation is if it's a linear transformation, we can actually denote it with a matrix. So let's take a look at either a shear or the scaling transformation and see how we can denote it as a matrix. Let's look at the scaling transformation as an example. And what we could do is, what Alan was looking at is suggesting is to take a look at what happens to the I and J components of this. And if we put x is equal to 1 and y is equal to 0 in this case, I would have, what would I have? Ax and 0, right? Wait, what's x equal to? X is equal to 1. So that's just a 0. And then if we take a look at what happens to the j component, x is equal to 0 and y is equal to 1. So this should just be 0, comma b. So it turns out, we'll see in hopefully in a theorem or a definition or some sort of property, is that if we let A be a matrix, where the first column and the second column are the inputs or outputs, are the outputs of your Ti and your Tj vectors, then A will represent the transformation. So A will represent the transformation, and then you can use this to perform your linear transformations. Only if it's linear. So in other words, if we were to try to do this with what's our first example? For the polar coordinate transformation, we wouldn't be able to come up with a matrix to represent the polar coordinate transformation because it's not linear. But if it is linear, we can, and the way to do that representation is to take a look at what happens to the standard basis, the ij basis vectors. And so that, I think, hopefully is stated here in this theorem. So if you have your standard basis vectors and you have a transformation, then there exists a unique matrix A such that the transformation T can be represented by A. And instead of saying the T of your X vector that you're putting in as an input, you're going to say the A times the X vector that you're putting as an input. And so A will be an m by n matrix whose jth column is the transformation evaluated at the jth standard basis. So in our example, the first column of the matrix A is the transformation evaluated at the first standard basis, 1, 0. And then the second column happens when we translate or transform the second standard basis vector, J. So your matrix can be represented as the T of each of the standard basis vectors. And so this is called the standard matrix for the linear transformation. Okay. Any questions so far? Yeah.
So if you were to get a problem like this on a test, what would be a good way to kind of, instead of like memorizing all these different transformations, would there be a way to derive these transformations?
Well, memorize. What's memorization?
So we're supposed to memorize it?
I don't know. I'm looking for an example that I would probably give you in the test, and I can't really find one right now. Well, let's see if I can make one up. So let's see if I can make up a transformation here. Let's make up a transformation that goes from R3 to, I don't know, R5 or something. So example, let's make up a transformation that goes from R3 to R5. And let's say my transformation takes a 3 vector, x1, x2, x3. And then it's going to output a 5 vector that uses x1, x2, x3. So let's say the first vector, the first component of your 5 vector is going to be x1 plus x2. And then the second component would be 3x2 plus 5x3. That's probably good. And then the third component would be x2 minus 4x3. The fourth component would be x3. I'll just say x3. And then the fifth component would be x2. I don't know, something like that. This is some random example. And now I'm going from R3 to R5, which means that we can't visualize it anymore. But I'll say that this is going to be a linear transformation. So first of all, I would expect you to be able to prove that this is a linear transformation. by putting in an x plus a y vector or something like that, and somehow showing that this is going to be tx plus ty, and then scalar multiple and show the works of how to show that this is a linear transformation. So say show on your own, you show this is a linear transformation. I used to get that a lot when I read textbooks, math textbooks. They say it's up to the reader to show that this is true. So that's kind of like what I'm doing. So, but I want to, the example here is to show that this is, if this is a linear transformation, which it is, which you'll show on your own, then that means this is going to be, this can be represented as a matrix. And so let's see if we can represent this with a matrix. And the way we'll do that is that since this goes from R3 to R5, we're going to be curious about what happens to the standard basis vectors in R3. In that case, it would be the ijk vectors 1, 0, 0, 0, 1, 0, 0, 0, 1, and see what happens to each of those vectors. So ti is t of 1, 0, 0, and that means x1 is 1 and everything else is 0. So x1 is 1, looks like this is going to be 1, and everything else has x2s and x3s. Oops, there's 5 of them. So everything else would be zeros. The next is j. Oh, that's not a j, that's a semicolon. Just a comma. All right, so t of 0, 1, 0. So x2 is 1 and everything else is 0. So I will get a 1 for the first one. X2 is 1, so I'm going to get 3 for the next one. X2 is 1, that's 1, 0, and 1. So wherever I see an X2, I'll replace it with a 1. And wherever I see an X3, I'll replace it with a 0. And there's only one X1. All right, and then finally, TK, what happens is 0, 0, 1 when x3 is equal to 1 and everything else is 0. I will get 0 for the first one, 5 for the second one, looks like negative 4 for the third one, 1, and then 0. So if I just take these as column vectors for my matrix, then I will have my matrix representation for the linear transformation. So that would be 1, 2, 4, 1, 3, 1, 0, 1, and 0, 5, minus 4, 1, 0. So this is a what by what matrix? This is a 5 by 3 matrix, right? Notice the 5 and the 3 in your transformation definition. It takes the dimension of the range of the codomain, and then it takes the dimension of the domain as your first and second numbers. And if we were to say what happens when we do t of 1, 2, 3, this should equal to what happens when we let a apply to 1, 2, 3, when we let a be multiplied with 1, 2, 3. So we can check that. X1 is equal to 1, x2 is equal to 2, and x3 is equal to 3. So this would be 1 plus 2. This would be 6 plus 15. This would be 2 minus 12, and this would be x3 is 3 and x2 is 2. That's a 21 there. All right, and if we do the matrix multiplication, we should get the same thing. 1, 1, 0, 0, 3, 5, 0, 1, negative 4, 0, 0, 1, 0, 1, 0. And apply that to 1, 2, 3. We're going to get 1 plus 2 plus 0. We're going to get 0 plus 6 plus 15. And we're going to get 0 plus 2 plus negative 12. We're going to get 3 and 2. So they are equal to each other, and that's not really a proof, but this is just to illustrate that the transformation and the matrix are producing the same results. Right? And because it's a linear transformation, we should have known, and this is sort of a justification for the theorem, is that t of 1, 2, 3 is essentially t of 1, 1, 0, 0 plus 2 times t of 0, 1, 0 plus 3 times t of 0, 0, 1. Because it is a linear transformation, we can take this 1, 2, 3 and break it up to 3 different vectors. And the vectors are really, 1, 2, 3 is really just a linear combination of your I, j, and k. Ti plus 2 tj plus 3 tk. And then so we can write it, because it's a linear combination, it just kind of splits up like that. And then that's how you can try to make the relationship between that and the matrix and how that splits up. The matrix is a linear transformation, or represents a linear transformation as well. Yeah.
How'd you get the 321?
What did I do? This first one or the second one? Because I kind of looked at two different ways. So to get this first number over here, I would get this and this multiplied. So 1 times 1 plus 1 times 2 plus 0 times 3. And then I would go on down the line. I don't know if we've actually done this. Kind of assuming that you know this. We haven't really, yeah. Yes. So it's 0. It's going to be 1 at whatever spot it's addressing, and then zeros for the rest. And that is what we would call so if you're an R2 or R3, it's the standard basis vectors that we know from maybe physics, or maybe from Calc 3, maybe even in pre-calculus when we're dealing with vectors. But if it's an R4, then you're going to have, that's why they call it E1, E2, or E1, E2, E3. It's because when it gets larger, like in R5, you would have 5 basis vectors, and your E1 is going to be 1, 4. Your E2 is going to be 0, 1. And then you can get the rest of your E's by just putting the 1 in that whatever spot it is, and then everything else is 0. Can't tell you. I have to admit, never really thought about that. But why is it an E? I don't know. That's, if you open up any linear algebra book, standard basis vector, E. And then you open up one that you like, it still have an E in it. And if you don't like any books, then too bad. All right. Randall, is that so? Did I talk about matrix multiplication much here? That's the idea of matrix multiplication. And now I think about it, I don't know if I've talked about it much, but that's the idea behind matrix multiplication. And in our examples, we're really just multiplying a matrix and a vector, and a column vector at that. In chapter 2, when we start doing matrix algebra, we'll formally define matrix multiplication between a random size matrix and a semi-random size matrix. And for now, our multiplication, our second matrix is always going to be a column vector until we get to chapter 2, which will be Wednesday. Okay. Yeah, and I think this idea that we are dealing with a linear transformation, and this idea that everything really just depends on what happens to the basis vector, is because that basis vector can take any vector in your domain and write it as a linear combination of those basis vectors. And then when you do that, you can just find your linear transformation by taking advantage of the fact that the transformation is linear. All right, there's more information in, let's see if we can do one of these problems. Just let's pick a random problem here. I don't know. Let's try number 17. Using the fact that it's linear, using the fact that it's a linear transformation, find t of 3u, 2v, and 3u plus 2v. So t of u, first of all, is equal to 2, 1. That maps 5, 2 to 2, 1. And t of v equals negative 1, 3. So to answer this, you want to know what t of 3u is equal to. I guess it would be interesting to figure out what u is, or 3u, but it's not necessary to this problem. But let's figure it out anyways. What is 3u equal to? 15, 6. It's taking your u vector and multiplying it by 3, scalar, multiplying it by 3. So not that we're going to need it, but that's just interesting to know. But we know that it's linear, so this is going to be 3tu, which is 3 times tu is 1, 2. So that's 3, 6. 6, 3? 2, 1. Thanks. All right, let's do the last one. T of 3u plus 2v. I guess we should do that one first, but let's just work this out. You should figure out what this is equal to for fun. But this one is going to be 3tu plus 2tv. And This is 3 times 2, 1, which we got to be 6, 3. And if we had done the second one, we would have gotten the answer for this one also, but that's easy enough to figure out. So this is going to be 6 minus 2 and 3 plus 6. Oh. Okay. So that's there's some power in linear transformations and being able to do these computations, and it all relies on linear combinations. And if you can write something as a linear combination of something else, then we can define this transformation. So this transformation, we can have, what's it called again? We can have a standard matrix for this particular linear transformation if we knew what happens to 1, 0, and 0, 1. Can we find out what happens to 1, 0, and 0, 1? I'll let you guys figure that out. Standard matrix for, so the word standard here refers to the idea that it kind of relies on what happens to 1, 0, and 0, 1. If you think the answer is just putting 2, 1, and negative 1, 3 into a matrix together, that's going to be incorrect, because if we try putting in some of these values that we already know, you'll see that you're not going to get the same correct answer. And so think about how to do this and how to come back and recreate your standard matrix by rewriting or finding out what happens to 1, 0, and 0, 1, because that's what you need in order to come up with a matrix, is to look at what happens to the standard basis, the I and the j vectors. Okay, can you do that on your own? I have this this meme. I've been collecting memes. Let's see if I can find the meme. Just wasting time here now. Memes. Oh, it's not even here. Where is it? Facebook? No. No. I can't find it right now. It's got to be here, but it's not. Anyways, this is for this one's for pre-calculus. This is kind of nice. It's composition. Anyways, I'll find that meme and I'll show you. It has something to do when the book tells you to, it's up to the reader to complete the proof. It's like when the professor tells you, you try it, you do it on your own. All right, I think that's it. Next time we'll have a quiz and we'll start with chapter 2. The rest of chapter 1 continues to talk about linear transformations and the graphics of it. Focuses on R2 to R2, which is kind of like what we did with the graphing calculator program. But next time we'll start some matrix algebra. All right, after you take your quiz on row reducing.